I like a new life. I'm just like very clicky.
Good, good. No, go for it. We're gonna enjoy this quick side.
There's like a school made.
Yeah.
Okay.
Oh.
So like,
Yeah.
it's just watch.
Oh, right there. Your lap.
You should have moved this way. Yeah, sorry. Look, you're on camera. Yeah. Is that? Yeah, I'm still. There we go. Now you can. Thank you.
What you doing?
Or be off the spectrum. But he lives in Toulouse, which is his parents. Just staying with his parents. In his parents' house.
Where is it? Where, like, where you are?
So it's like where she was going. And she's long.
Oh, awesome.
Because you have to.
Oh, that's cool. Yeah.
And she's just like,
So you're in an MBA student? Like, I got
slightly. It changes.
Oh, okay. You're coming back.
Yeah.
I thought you were
Being under, even though she's like, it's definitely humble.
It's really probably
It's like constantly getting told that I'm good enough for pretty much. This person might be the
Just as a heads up, everyone, we'll get started in a couple minutes after people grab lunch.
So if you like don't get a job, they will tell you if you are just not instead of just like or you can just know that because it's
You know that, but also she was like, she just came out of high school and like was just eating his own way. Eating that way. Stop the elementary.
for like a authority to tell you that. She was initially planning to go to college and then she decided late.
And it was more like October of her senior year in college or in high school. She was literally scouted on Instagram and signed by an ING, which is like a worldwide agency. And like decided that she would apply to college after. No, I didn't defer. Which is actually a really good thing. Like, she was a good candidate, but like, without being like so exceptional in anything. Specifically, that this was like
Nope.
good.
Go ahead.
For my degree. It's really hard to get. How are you? And like, I had. I think I had. She didn't have it. Whereas, like, and then otherwise, it's like, you got
Was definitely
Hi, everybody. Thank you so much for coming to the third of our seminar series. We're excited that we get to present this machine learning coding workshop today. Without further ado, let's brief review about why we're here together. Health AI Network is an interdisciplinary community that began to address the need for a better visibility and also match of capabilities as well as needs in our healthcare ecosystem regarding the use of AI in healthcare. And to do that, our network has been trying this semester to first get everybody on the same page about what AI is, what are its potential applications, and how do we actually go about it in a sustainable manner. And this seminar series too is part of that educational initiative that we have started at Penn. And so today, this is a follow-up after our first seminar, which gave a high-level overview of currently available AI technologies and their current application areas. And then our second seminar that was held about 2 weeks ago on kind of the problem structuring as well as the relevant policy aspects, and also still to be worked out areas in AI applications to better our healthcare system. And our upcoming seminars after this panel today, after this workshop, we have a provider panel coming up so that people who may not be exposed so much to the clinical world may have a better understanding of what providers actually care about. What are the barriers really in implementing as well as adopting certain solutions in a meaningful manner? And then lastly, we will end our seminar series more venture focused. So we have invited founders of quite successfully funded AI startups that are still in business and as well as some VC investors. So without further ado, I'm excited to introduce to you our leaders of the workshop today. They will come up and introduce themselves as they lead their sections. But Eli, I'm curious, why are we here today? What will our audience walk away with?
Hi everyone, how's it going? So really what we want you all to walk away with is an understanding of how machine learning works. What does it actually look like for a data scientist to sit down and implement some of these algorithms? What's the output of the algorithms? How do you interpret that? And what's the most effective way to use these tools to improve healthcare? So before we get started, so just brief show of hands, who here is a medical student? Okay. How about a resident or fellow or attending? Okay. How about who's in boarding? And how about something else, engineering, graduate school? Cool. All right, so a pretty diverse crowd. So the most important thing if you're trying to make any new application in healthcare tech is to have a really well thought out, well motivated problem statement. And until you have that, you don't really know whether or not machine learning is the right tool to use to fix that problem statement. And Mike Dragelis, who's the chief data scientist here for Penn Medicine, he has shared with us this, what I think is a really useful framework for developing problem statements, which is to think, if I knew some piece of information, then I would do some intervention to improve some measurable outcome. And most health problems in healthcare can kind of be reformatted and reframed into this, this sort of outline. And in this case, information a lot of the times is something like detection or prediction. So if I could detect cases of schizophrenia early on, maybe I'd be able to do some intervention or initiate treatment earlier, increase social support, and then that would improve their health outcomes. But what's important, like in that case, there's not a super well-defined intervention. We don't have great ways of treating schizophrenia. So there has to be an actionable thing that you can do based on that information. And you have to know specifically what that intervention is going to improve. So here's an example from the ER. So if I knew which patients had intracranial bleeding immediately, then I could call neurosurgery ASAP, and that might improve survival. Another example would be if I knew which patients didn't have acute intracranial bleeding and I thought that they had a stroke, I could go ahead and push TPA, and that might improve stroke recovery outcomes. So I'm going to talk about an example of a startup called Cure.ai. And basically what they've developed is a computer vision algorithm to look at head CTs and classify the CT as one of several acute intracranial findings. So you can see on the right, these are GIFs that are from their website that basically show their algorithm's taken in a random CT, and it's basically highlighted where there's pathology. So in the top right, you can see that little red line around where there's an epidural hematoma. And then in the bottom one, it's highlighted as subdural. So that's pretty cool. And how did they get to this point? So they started with a training set of 290,000 head CTs, which is a really, really large data set. And then they tested their algorithms. They developed the algorithm on 290,000 CTs. And then they tested on 2 independent data sets. One was labeled by actual radiologists, and the other was labeled by an algorithm that just read through the EHR labels. And compared to humans, it was just as sensitive and slightly less specific. But overall, as a diagnostic tool, their area under the curves are fantastic, like around 90 to 95%. So the blue line is the auto-labeled data set. It actually did better on the human-labeled data set. And then the black X's on there, if you can see them, are radiologists and how well they did. Now, here's another example. This one's from the OR. So the problem statement for this application is if I knew that a patient was going to become hypotensive soon, I could deliver drugs or fluids to improve the vulnerability to ischemic events. So this other company, they developed the Acumen Hypotension Prediction Index, where they basically take arterial line waveforms, generate a bunch of features from the waveforms, and feed them through a machine learning algorithm. And that tells you either 15 minutes, 10 minutes, or 5 minutes out, what's the chance that this patient is going to become acutely hypotensive. And it works pretty well, above 90% sensitivity and specificity at 5 minutes out, which is pretty good. One thing to note is the training data came from the OR and the ICU, but they only tested it on data from the OR. So some questions that remain, one, like I said, we don't know whether this actually works in the ICU. We've only trained it on ICU data. We don't know, does it work in that context? We also don't, the intervention is pretty unclear as well. Giving fluids or drugs, it's unclear whether that actually is going to help. If we really know that giving physicians a lead time and intervening earlier, will that actually improve survival? Another thing is that most patients don't have A lines during surgery. So the clinical population that this is focused on is somewhat unclear. And this raises a really important question is if you have an algorithm that performs really well at the task that you've trained it to do, that doesn't necessarily mean that it's going to be clinically useful. Maybe so this is the actual device that they built, and basically you have a meter that shows what's the chance that this patient's going to become hypotensive at any given time. Maybe having that thing in the OR, flashing a number towards the surgeon, actually makes the surgeon perform worse. We don't actually really know until we've tested these things clinically in situ. So it's just sort of a word of caution. Don't proceed unless you have a really good problem statement. This is really the most important part. Machine learning may or may not always be the right tool. And to help you guys understand when it is the right tool and what are the mechanics of machine learning, how does it actually work, I'm going to bring up Zach, our lead data scientist here. Zach, take it away.
Hey, thanks, Eli. So, I am working on data initiatives at the Health AI Network. I'm an undergrad at math and computer science, and so I kind of want to take kind of what Eli has established, so we kind of have a problem statement that's very well formed, and kind of go from there. So, kind of for the rest of the workshop that I'm going to go over, kind of assume we have a well thought out problem, and kind of we're going to work from there as a starting point. So, so we have our problem statement, and kind of what is the next thing that we're going to focus on, right? And so is really a data collection and cleaning phase, because what kind of makes a machine learning algorithm kind of unique, right, is we have to go through this sort of in-depth training process. So we have to have a large data set to train on before we can kind of be guaranteed that our machine learning algorithm will be able to perform in a real life clinical scenario. So really starting off identifying all the relevant data points, kind of the ML lingo, they're called features. And then we can kind of collect the identified data points called features and then put them into a structured format. So really kind of want to emphasize that this process can be quite time intensive, especially kind of the collecting of the data and putting it into a structured format. It really kind of depends, but like especially 2 and 3, they can vary in terms of difficulty. I kind of wanted to just give kind of an example of what this cleaning process actually is. So let's say we have a bunch of data, and kind of one of the challenges that comes up quite a lot is like handwritten doctor's notes or kind of this plain text. And so I kind of have an example here, like John's a 24-year-old patient, admitted to the hospital earlier today, right? And so it's kind of unstructured, right? It's a lot of different points of information that are kind of independent of each other. And so when the data is in this format, you can't use your favorite machine learning algorithm on it, it's not going to work. So what you have to do is kind of convert that into a structured format where, for example, we have a bunch of fields like a name field, an age field, and a time admitted field. And so this is going to be really important to either one, kind of unideal case where you start off with fairly unstructured data, but really if you're kind of thinking about this from a kind of zero to start, you really want to think, how can I put the data in a structured format right off the bat? So, yeah, and so then just an idea of what a nice data set to work on would look like, kind of have a data set of patient admitted, or kind of like time series data on patient life. And so again, as you can see, we have these like atomic fields of like age, time admitted, time discharged, and so on, as well as kind of for the files, we have a timestamp, so kind of at what time were these files taken, and then kind of just these kind of one number that represents the level. So, or the vital, sorry. So it's going to be really kind of helpful to have your data in this format. So kind of one of the awesome things about PenMed, right, is that they've been kind of thinking about this for quite a long time. So since 2011, they've been kind of collecting data as well as cleaning it. And so this is a figure from Mike Vergalis, who is working here at Penn Medicine to really kind of try to apply these ML techniques within a clinical setting. And this is kind of some of the data that he's collected. Kind of, hopefully, it kind of can show you guys, right, that there is some data and there's some stuff to work with already. So maybe not, in a lot of cases we can pick, create a problem statement, identify the data, and not have to work a lot to collect it. And then one of the last things I want to talk about is label collection. So a lot of the times with the machine learning problem, right, you want to predict something. And so oftentimes like a diagnosis is something that you would want to predict. And kind of what that means in this kind of collection phase is we have a bunch of, for example, patients, and we want to attribute a label to them. And so this can be a time-intensive process because, especially in healthcare, we want an expert to make the diagnosis. So oftentimes label collection can be kind of another time-intensive part of this process. And one kind of cool direction that a lot of people have been exploring is this notion of like crowdsourcing diagnoses within kind of an expert network. And so if you kind of come into this roadblock, that's definitely kind of a nice alternative as opposed to kind of all doing it yourself or within a single lab. So kind of at the end of this section, right, kind of what do we want, right? We want a data set that's very structured, as well as kind of having these relevant features, and then kind of accurate labels. So kind of at this point right now, we have a problem statement as well as the data, the relevant data to go along with it. So now we can really kind of jump into the machine learning proper of the talk, right? And so for maybe the next 5 slides, I'm kind of going to go over some like basic terminology of machine learning, kind of how to frame problems within the space. And so I think kind of at a very high level, right? So machine learning kind of as a subset of AI has a bunch of subfields within that, kind of depending on what task you want to do. So I just kind of listed 3 here that are quite common. So image recognition being probably the most visible, especially within like the pure ML community. The kind of image recognition has gotten really kind of incredible. Just like given a picture of a dog or a cat, the accuracy is really high. And so, you know, for a clinical problem, this is a lot of X-ray imaging can be used within the existing sort of tools that have been developed by ML researchers. And natural language processing, which kind of like think maybe Siri, probably Alexa. So kind of anything that has to do with like written or spoken language, kind of natural processing is really kind of the subdomain. And then there's clustering, which is sort of, you know, finding similar sets of data. And so I think really if you can kind of identify a task within like one of these three areas, for instance, it's going to be really helpful to learn kind of, again, like read up on the background, because like natural language processing is a quite developed field. And so really kind of trying to get some ideas from what other people have done is going to be really helpful. Cool. So now really how are we going to frame this problem that we have? So at this point, right, we have data and then kind of an information, an intervention, and outcome. And so kind of what we need to do on the machine learning side is sort of pick kind of a paradigm, right? So the two main ones that you guys should be concerned about are unsupervised and supervised learning. And so the difference, you guys have water. Oh yeah, thanks. Yeah, of course. Can you hear me now? Cool. Yeah, sorry about that. So right, so we want to frame a learning problem, and kind of our two options, right, are unsupervised and supervised. And so kind of the primary difference of these two is one has labels and one has no labels. And so maybe to kind of make it a little bit more clear, so supervised learning is sort of you have an input and a desired output. So kind of the input being your data, the output being a label. And so how it's going to work, and I'll go into more detail later, is you get a bunch of examples of inputs and outputs and you train on it. And then you want to have an input and then you want to predict. So kind of the idea being you learn on a bunch of like this ground truth knowledge, and then you want to reproduce your ground truth with kind of new data. And so a lot of the sort of classification problems, especially like the ones that Eli was talking about, were examples of supervised learning. And so then kind of the other one being unsupervised learning. And that's kind of how do you find hidden sort of patterns in your data. Oftentimes like clustering algorithms are going to be a really prime example of an unsupervised learning algorithm, where in a clustering algorithm, you pretty much have a bunch of data and you just find a certain number of clusters. And so given a new sort of patient or a new example, right, you can say which one of these clusters is located. So yeah, so I guess you pick a learning paradigm, right? And then after that, we can pick up. And so kind of the model is the core of the machine learning. You can think of it as like a mathematical function that takes a feature, so a row of features, so again, like a patient, and then returns a prediction, whatever you're trying to do. So example, you know, like a picture of a dog, we're doing image recognition, and you want to kind of spit out the label dog as being the correct answer, right? And so what actually does this prediction is this mathematical function. And then kind of the interesting part about it, right, is that you can train, so it can kind of learn. And so kind of it might be a little bit vague, but we have these parameters that train as you train your model, and so the model gets better over time. And so then kind of to give you concrete examples, right, we have logistic regression, neural network support vector machines, k-means. So these are all specific examples of machine learning models. So kind of for a specific application, one of the really important questions is sort of which model you're going to pick. I won't go into detail the difference between models, but usually that's going to be something you want to spend a lot of time thinking, kind of what is the model for my question. And a lot of times at this point in the process, you want to bring in a data scientist to kind of inform you on that decision. So one thing I wanted to note here, which is quite important for ML and healthcare specifically, is issue of model interpretability. So kind of the idea being, and really kind of this is like two pretty good examples of a model that is Stand on mic, sorry. Um, so the tree diagram over here, right? So it's like if we want to, diagnose a disease, we could say, okay, like follow the tree, and then at the end it'll have a sort of positive or negative result of that diagnosis, and we can kind of trace how exactly the decision was made. And so kind of contrasting that with over here is it's a neural network, which is a model. It's very much like a black box, right? So you can make a prediction, but you can have really no idea how it was made. And so oftentimes what kind of machine learning researchers do, for example, again, like image recognition stuff, they use these like neural networks, which are kind of best in class, right? But they're black boxes. So really kind of trying to think about, do I need to understand exactly how my model makes a decision is going to really inform which model you pick. So kind of something to keep in mind. Yeah, so actually, let me stop here really quick. So any questions? Is this all sort of making sense? A lot of ground. Cool. Okay, I'll keep going then. So we've selected a problem statement, collected data, picked a model. So now we're kind of ready to go about training and testing our model. And so what that really entails is starting off with our data, it could be labeled or unlabeled, and splitting it into three parts. So one is a training set, another is a validation, and then the last one's a test set. And so the training set is actually, it trains the model, makes sense. And so usually over kind of a period of quite a long time, up to hours to days, we take a model, we kind of feed it the data over and over again until these parameters that I mentioned before are kind of in this optimal state, so we're making really accurate predictions. So pretty much, yeah, so it's this process of training, and then kind of this validation and test data are what we're really using to evaluate our models. So the validation is a little bit beyond the sort of scope of this talk, but it tunes the model further, and then really what you're going for, right, is good test performance. So you train your model, and then you have a bunch of test data. And so the difference between training data and testing data is that you don't have your sort of label when you have your test data. So you hold that to the side, and then you just say, okay, like model on all of this new test data, what is your prediction? So you compare sort of the prediction versus the ground truth, and that's how you can get your accuracy, your ROC curves, sensitivity, specificity, and kind of all those sort of key metrics to really evaluate the success or the failure of this model. And really kind of this accuracy and ROC curves are really going to make a lot more sense again if you have a really kind of well-defined problem statement, because it kind of identify like what is more important, like sensitivity, specificity, accuracy, etc. So yeah, so let me, a really quick summary. So we're kind of going to pick a framework, and then within that framework, pick a model. Then we kind of split our data into three different sets, train our model, test performance, and then oftentimes it can be an iterative process, so keep kind of cycling through until we have a test performance that we're really kind of happy with. And then we can use the model for real world inference after our test performance is kind of at the level that we need to be. So one more thing I wanted to mention, right? So deep learning. Really, a lot of the state-of-the-art machine learning performance is done with sort of some of these deep learning models. And so, kind of as I just said, like what deep learning is, or kind of what it means, is it's a type of machine learning model. So just kind of like a mathematical function, and it kind of has some pretty cool features to it. Kind of the characterization that I would give, right, is it's kind of a black box that really takes a huge amount of training data, more so than really any other type of model. And it kind of requires that it's run on special hardware. And so kind of these are maybe some downsides, right? But at the end of the day, what you get is a lot of times just amazing performance on like recognition, image recognition, natural language processing, kind of really, a really impressive performance. So a lot of times it's sort of worth the trade-off. So kind of the last thing I wanted to go over really quick is, just kind of what does it look like from a programming level? And so we're going to keep this kind of very high level, but just kind of to give you guys a sense of like, what is a data scientist actually going to do? So really, as you can see here, what we're doing is we're just reading reading data and labels, right? So this is, we have all of our data collected, and now we want to read it. So it looks like, in this case particularly, we have our data in a CSV file, our labels in a CSV, and then we read them. And so now we have a variable called data and labels. And now, so this is defining our model. So in deep learning approaches, we call them like a model architecture, but really what this is doing is just creating a neural network. And so I won't go too much into depth, kind of what each layer does, but kind of you can see here, we're calling like, well, first we like have this model, right? And then we call model.add dense layer. And so what that's doing is it's just making, so like each one of these in kind of the graphical depiction, right, is a new layer. So we're just kind of adding layers. So this, at the end of this stage, right, what we have is a model and data, right? So now what we do with our model and our data is split it into a kind of test, validation, and train set. And so there's probably a lot of detail here, but notice what we have now here is test size. So this is saying we want 20% of our data to be test, 20 to be validation, and then there's just kind of a method that's already defined, this train test split. So we give our data to this train test split, and then what we have in return, right, is sort of our training data, our validation data, as well as our testing data, test X, train X. So again, we partition our data, so now what we can do is really train it, right? So what we have here is this model.fit. That is kind of the training, kind of some libraries call it fit as opposed to train, but it's kind of the same idea, right? We pass in our data, so our training data, train X, and train labels, and we just train. So this is going to be the most time-intensive part of the code. We're just going to kind of keep training until we have really good performance. And then I'll kind of gloss over the bottom here, but what we're doing, right, is we say model.predict with our test data. So this is going to be like evaluating how good our actual model is performing. And then kind of again, high level, right? So this AUC method creates all the points for an ROC curve, like area under the curve, right? And then we're just plotting it here. So at the end, once all this code is ran, it's just going to show an ROC curve that gives you like the sort of the performance of the model, as well as probably you might want to look at accuracy as well as sensitivity, specificity. So this is kind of what it looks like from really a sort of a coding. This is what a data scientist is going to really play around with. For example, one of the things that data scientists play around with, again, is creating this model. So a lot of times it's like how many layers you want to add is something that a data scientist has to really think through. So with that being said, I really want to hand it off to Ahmed. He's going to go over sort of potential pitfalls and give you kind of a really concrete application.
All right. Okay, so before we move on, I wanted to recap kind of what Zach said in like a real life example that we can do really quickly. In our case, let's just say that we had an image. In this case, it's a brain MRI. So I'm using this software called ITK Snap, which is free. It's open source software. So let's just say I have a brain scan of a patient's brain scan, and my goal is I want to measure the volume of the patient's ventricles in order to make some sort of decision down the line. So using what Zach told us, so what is, in this case, we can represent each of those pixels right here. Those can be represented as instances, or basically separate data points. And each of those data points has two types of information in them, two types of features that we can use. One of them is intensity. So here, for example, it's 468. And the other here is the position of the actual voxel. So let's just say that I want to segment or color in those ventricles so I can measure the volume. And in this case, we're going to use a machine learning algorithm called random forest. Basically, what we can do is we can highlight the part right here in the scan we want it to use, and then we say we want to give it. So using classification, and we want to give it some training data. So training data is basically labeled examples that we're providing for the algorithm. So we're basically telling the algorithm, this is ventricle, this is not ventricle. So it can focus and learn that so that it's able to segment the entire ventricle. What I ideally want to do is have small amounts of labels so that when it doesn't see, even though it doesn't see the entire image, it can quickly figure out which is which. So here we label this as ventricle, we label this as ventricle, ventricle, one slice, and then we say this is not ventricle, this is not ventricle, this is not ventricle, and we say train classifier. And what we get is some sort of speed map. So it figured out, you can tell right here, it figured out pretty quickly, this is ventricle, this is ventricle. And if we, the next step is, okay, I want to use something like active contour to fill out that it's guessing, okay, I think this is ventricle. And so what I can do is I can add, let's see if it continues up there as well. And I can do something like this, and bam, and then we see in real time filling in that guess of what is ventricle, what is not. And the beautiful thing about this is just it took a few instances, a few voxels that we've labeled. We've added those labels to it. So if we want to take this to a clinical setting, you can say a patient has a flu. The features would be the symptoms. The labels would be sick or not sick, flu or not flu, flu versus allergy. That would be the label. And then finally what we get is some output on the rest of our data. So here we can see a beautiful lateral ventricle segmentation. So that's a supervised case because I provided a label for that image. So let's just say for an unsupervised case. So let's say like, you know, I want to. So this is software you guys can download online and play with it if you want to. So let's just say I want to do an unsupervised case. So in an unsupervised case, I don't have any labels. I don't have any clue of what exactly I want. And what I want the algorithm to do is be able to bin based off of features. So it's going to separate it into groups or clusters based off of features. So in this case, let's just go back to this, and let's just see what happens when I use an unsupervised. So this is clustering. So with an unsupervised, what I do is I can set the number of clusters. So I can set the number of clusters. So in this case, I said, okay, I want it in 3 bins, or 3 clusters. And so it started to cluster based off intensity and based off the location. If I decrease the clusters, it starts to bin off between, this is obviously based off intensity. So you can see the blue here is when the intensity is pretty low, and otherwise, if it's above a certain threshold, it clusters it together. As I increase the number of clusters, you can see that it can start to get more and more refined. So it starts here, for example, it's trying to get the white matter in the brain and trying to get those tracks. Then I can move on and say next, and I can add the bubble and see the bubble expand, and we're all happy. So, okay, so that's a real life example of what I did. So what I did is basically provide a set of labels for a specific set of data points, and then I tested it on things that I did not see before to get some sort of performance out of it. But there are 3 major pitfalls, or 3 potential pitfalls that we have to keep track of while we're training these machine learning algorithms, while we're gathering those data. So we have a good task, a good problem, we have a good set of features. Now let's figure out what are the pitfalls. So the first pitfall is training on the wrong data and testing on the wrong data. And this actually happens a lot more than you think. And this is when you train, so you say, in our case, I picked a few pixels that I said, you know, this is ventricle. So imagine if I trained my algorithm on the same set of pixels that I picked out and said this is ventricle. Well, the performance is going to be wonderful, but it didn't really tell me if it's able to predict or not. And in this case, for example, if I train on my training set and then test on my testing set, all that does is tells me that the model is able to separate the data points, but it does not tell me that it's able to predict whether or not it works or not. So sometimes you'll get a very beautiful curve, and you'll say, "Whoa, I can clearly." Clearly based off of this, I can say that my model is able to predict that someone has the flu. But in fact, what it did is just it memorized the data and then give it back to you. The next issue is with experimental design. Often when we're trying to predict something, we should collect data before the thing happens. And sometimes what happens is people end up, when we're researching, we end up collecting data when it happened. So how can I predict? How can I train my model to predict something if I don't give it the right amount of data or the right data to use? So those are 2 things to keep in mind. So interpret the performance on the testing set that the model did not see, and make sure that your experimental design is good. The next pitfall is overfitting. Overfitting is basically when a model is so powerful or the model is able to capture the data. So here's 3 examples, right? So this is, I would say, underfitting. The model is not, so this is a linear regression, for example. And this is, it fits perfectly. And here it's fitting, well, it's actually fitting perfectly, even better than it's fitting too good. And in this case, we have a case where it's overfitting. Overfitting means, for example, if I'm a student and you give me 10 questions, and then you come back and you give me the same 10, a different 10 questions, but they're pretty much close or the same to it. Well, you don't really know if I actually learned the material or I just memorized the question. So what's happening is it's able to memorize exactly where those data points are. And so there's a trade-off between this. It's called the bias variance trade-off, where I have a high bias and I'm not able to fit very well, which is all the way on the left. Or if I have a low bias but high variance, I have too many parameters that I can sort of make my curve bend in all sorts of ways. I can capture data perfectly, but I know I didn't really capture that natural function that I'm trying to model with my machine learning algorithm. And so there's ways to avoid this. And one way we can think of it is, well, there's like this sweet spot of complexity. If your model is too complex, it can capture a lot of information. It can fit the data perfectly, but it's not really modeling the correct function. It's not really modeling the function in nature that we're trying to estimate with our machine learning algorithm. And then the third pitfall, okay, this is, people stuck around, this is good. All right, so the third pitfall is, if I go in with no hypothesis, no rationale, if I go in with that, just remember, we're trying to model a function that already exists in nature. If I have no hypothesis or rationale, if I'm just saying, look, let's throw it out the model and see what sticks, I might get good performance. Something might stick. By the end of the day, it's just a lot of baloney. So what you really need to make sure is have a solid hypothesis, have a solid rationale. What we're trying to do is basically do pattern recognition using these machine learning algorithms. So ultimately, what these machine learning algorithms are about is pattern recognition, not necessarily giving us answers. So if it spits back that anyone in a tuxedo has the flu, that's probably not a correct prediction, but you'll get that answer if you don't really have like a valid hypothesis or rationale and you're just feeding it tons and tons of information. And with that, we'd like to move on to and say, what can AI do for you? What kind of machine learning problems can we solve? And I think Eli, you're gonna lead the brainstorming session.
Right. So before we move on, any questions? Okay. All right. Good. So everything made perfect sense. That's great. So yeah, what we want to do is just have everyone kind of group together with like 3 or 4 people next to you and try and come up with a problem statement that you think could be addressed through a machine learning solution. And then what we'll do, we'll give you guys like 5-10 minutes, and then we'll get back together and we'll discuss the sort of best ideas. And yeah, just rules for this. There are no dumb ideas. Just say whatever you think might work. Quantity over quality, and just try and build off of each other. So yeah, go for it if you're interested.
Any ideas, gentlemen? We're over like oh wow, result where you actually see something I surprisingly have not. But you can assume for
It made it more workshop-y with
You can't always do it.
that.
Yeah.
So it kind of does the screen. So that, yeah, basically results, it tells you what you do more on top of that, so you kind of make some research.
Okay.
Everything. Technically, it's so many things that I mean, today that you end up looking for so should you problems with my I guess the thing is it's marketing like everything. And the question is, do you go for like more serious and you and I have no idea but this you might cover information, you might see something important. And then the question is, what is more important? Like specifically something that might be margins, or you just want to be average or accurate in the way direct. So the things some people I think there's like a very symptomatic, like because we're trying to figure out stuff, they might actually go something more. Because these guys like they're tradition, they practice. Of course, and I think by the way, both make sense. For a specific day, every sales not so it creates here. And then from those results, we get also queries, and that's
All right, guys, we're gonna group back together. All right. So, any teams want to raise their hands and share their problem statement? No.
So everyone has ideas, or like is the problem like no ideas? The problem is like ideas, but it's too valuable to share. That one? Okay. This is I mean, you know, the other saying is ideas are cheap. So. I mean, does anyone want to discuss any idea that they came up with? Yeah, go ahead.
We don't have a problem statement, but we talked about like something that would essentially take kind of like broad level, basically like it would lop off, like if people have like a flu or a cold or whatever. So I don't know if that's like an advanced like wearable or something, maybe just like it's a time sequence of like vitals or something that, hey, this thing can basically take your kind of like everyday like garden variety illnesses and be like, you don't need to go see a doctor, like predicted you're this, just, you know, that way like doctors focus on like real issues.
Okay. So I guess then if I knew that, if the patient knew that they were not so sick, then the or lack of intervention would be to improve, I guess, their quality of life. Would that be the statement?
Reduce burden on
Reduce
ERs.
Reduce burden on medical services.
So it'd be like a ruling out.
Yeah.
As well as maybe some.
So like, what are some features that, you know, you would use? Like, what are some like, you know, features that have a clear hypothesis or rationale that you would use to sort of solve that problem? Anybody? I'm gonna start picking on medical students. Okay, so I'll throw in one. So I think like heart rate, for example, is like like one of all the vitals I think would be useful, because if my vitals are way off, then it doesn't matter what I have, I should probably go to ED. Way off for no good reason, I should probably go to ED.
Temperature would be another one.
Yeah,
There's some way that you can non-invasively measure that with like a wearable or something. You saw someone's temperature over time. That would tell you something.
So here's like an actual problem statement that we got from the UPHS system. So one problem is in the ED, there are folks that come in frequently, and they should be fast-tracked. And so they want more on the, I guess, you want to be more efficient as an ED. So that's like a problem statement. If I knew someone was on the fast track, then I would place them on the fast track, and that would improve overall, you know, ED workload, or overall, I would improve, you know, resource allocation. So that's not necessarily clinical side, but I guess more on the like how do you management side. Like, what are some features that you would use in this case? There's no wrong answer.
Just that they've been here a lot. Right?
Okay, so I got
the medical record would say you've been here this amount of times or experience.
okay. So one feature brought up was frequency of how often they visit ER.
Doesn't matter if they've been there for the same symptoms, same problem.
So like frequency in terms of problems and symptoms. I'll throw in a crazy one. What about the facial expression? Just facial expression. Can we determine if someone's sick or not? Some doctors say like, I just look at the patient and I can tell if you're sick or not. Believe it or not, that's actually been said before. Yeah, they like look at it like this person's sick. I can tell. Or like a nurse would say, I can tell this person's sick. Yeah. That's what people say. That's what we say. I mean, it's not good in court. Like if you're on jury duty and you say that, that's a disqualification. But apparently, if you're in medicine, that makes you a better doctor. If you can identify someone sick quicker, then that means that outcomes are probably going to be a little bit better.
If
you want to take like sweat buckets and be able to like determine through that. So,
Okay.
take a big sweat.
Sweat buckets.
It helps with temperature and everything, the skin temperature
Yeah, that's
too.
true.
Because sometimes skin external temperature can be different than internal.
So that's a good hypothesis and rationale. It's using sweat buckets to generate sort of a new kind of data that we don't usually collect. Does everyone feel comfortable going out there finding problem statements and coming back to, like, now they know, like, the whole point of this is to get one thing across, which is what's a good ML problem, what's a good problem statement, what kind of data do I have lying around that I can use to, that I can organize and clean up so I can find a data scientist to start a project. Is everyone comfortable with that? If you're not, it's totally fine. After that, I start charging money, so.
So the point of this hour really was not to learn how to code, but for clinicians, medical students like us, as well as people who don't code in business or any other disciplines, to at least know how a data scientist thinks and talks, so that when we do have a conversation that leads to a collaboration, that we are in a better spot in understanding each other's needs to collaborate better. As a follow-up of this, if you are actually in practice and you have a clinical problem that you want to work on, you have a patient population that you care about and you want to impact over the next 6 months or 8 months or a year, and you have access to relevant data, then we will be actually opening up a program for a clinical champion to enter their problem with a proper data set. And we will match you with data scientists as well as business talents to scope out the problem into a solution and make that sustainable. Hopefully. Thank you for joining us. And our primer, as well as the content from this session, will all be coming available on our website, healthainetwork.org. So thank you and enjoy the rest of your day.
Thank you.